Machine learning algorithms are often trained on historical data, with some exceptions. In most cases, the trained model is placed into production and real-time inferencing begins. That's a big success for the team that delivered the model. But unlike a typical software delivery, the model can begin to drift almost immediately. When the world suddenly and abruptly shifted to become more physically distributed, no one told the machine learning algorithms that were out there in production. And as a result, many of those algorithms went just a little bit haywire.
I'm Ravi Parikh. I'm a medical oncologist and assistant professor at the University of Pennsylvania and at the Philadelphia VA Medical Center.
Well, thanks for joining us today.
Thank you.
Can you tell me a little bit about your broad research interests? What are some of the things you're studying and doing research on?
Sure. So a lot of my work, I run a lab that focuses on using machine learning, developing and implementing machine learning based predictive tools in clinical care to shape clinical care delivery. I have a particular focus in the oncology and advanced illness populations, developing predictive tools that can be used at the point of care to help direct things like palliative care consultation, end of life planning, or broader care management support. But our team runs trials in everything from cancer screening to opioid harm reduction to other areas of clinical care as well, just generally focused around how we can use machine learning based clinical decision support to help improve clinical care delivery.
I hope most listeners to Data Skeptic will already be aware of how much effort and good results have come out of the application of machine learning to medical use cases. But at least what we've covered more on the show is sort of the research side, how we go from data set to a typical ML workflow and come out with some classifier. What I don't always get into is sort of what you might call the last mile of machine learning, how we take the result we got trained in a notebook environment or wherever and actually make it useful for doctors and clinicians and people like that. Can you talk a little bit about that process?
Yeah, I would say that that's what the majority of our lab's time focuses on, is on actually getting down and talking to end users about how we can develop predictive tools in a way that influence clinical care. As an example, I collaborate very closely with a team of qualitative and mixed methods researchers, behavioral scientists, and implementation scientists, kind of broadly classified under sort of a human factors portfolio that actually gives some insight into how machine learning based tools can have maximal impact. Particular areas that I think are really important to elicit from end users involve things like threshold setting, visualization of data predictions, and how we can tie in better predictions with other proven behavioral economic strategies to motivate clinician or patient behavior change, including things like peer comparisons and performance reports. So all of that, I think, ties in and is commonly ignored in ways that machine learning is deployed in clinical care. And that's really what we try to focus on, since we're interested in having clinical impact.
Are cases like that a situation where we just need a little bit more heavy lifting and elbow grease on the machine learning side to get the features into the system? Or is there something that really requires an intrinsic human in the loop here?
I really think that human in the loop based models are going to be most successful in healthcare. And so I think more than getting at the right features, which obviously is important, I think having a human in the loop for the initial deployment or the conceptualization of deployment is really helpful. I'll just give you an example from my own clinical experience. So when I was a trainee in my hospital, we went out to deploy a new electronic health record. And so one day we just transitioned from our old EMR to a new EMR. And so the day that I walked into my hospital wards, there was this new dashboard that came out that listed all of our patients on the wards. And at the end of that dashboard, there was this new column for a risk score. And supposedly it was a machine learning based risk score that was proprietary to EMR and predicted someone's risk of readmission. And supposedly it was pretty accurate. It had been validated and had used commonly available EMR features, but was validated to predict risk of admission. The problem with it, it was deployed as basically a red, green, or yellow for indicating risk of readmission on that column. And so the way it showed up was, I could scroll over to that list and look at their risk of readmission. I was on the oncology, the cancer service at the time, and everyone's readmission risk was red, basically 100%. And we had no idea how to use that information because everyone knows that everyone's on the oncology ward was sick. But if you follow this EPIC-based risk score, you would just never discharge the patient from the hospital because everyone had high readmission risk. So I think it's an example of how having a clinician in the loop and actually sort of either tailoring thresholds or changing the way that risk scores are presented could have enabled the most clinical impact from a probably pretty good score like that. In the end, most of us clinicians found the red, green, yellow to be distracting. We actually eliminated that column from our dashboards because it was just not useful to us. I think having a clinician in the loop beforehand to maximize impact could have been really helpful and serves as a good example of how we could optimize machine learning in broader aspects of clinical care.
So when I hear about a situation like that, I wouldn't label it a failure. I would label it like a learning experience. You took away that the actual people using the system don't want the color system. In this one case, maybe the score is confusing. That's great feedback for a machine learning practitioner who might now think of a new way to develop something or collaborate with you on the next great design. Can you talk a little bit about that process? What does it take to get these insights and have a feedback loop going?
Sure. I think starting from the portion of actually defining outcome, defining features that are important, and trying to optimize some of those features, I think having a constant feedback at the beginning is really important because where we as clinicians lack in some of the particulars behind model tuning, parameter optimization, cross-validation, I think we have tremendous insight to give into predicting the actual clinical outcome that is most likely to be actionable and defining the right features. Just as an example, I work very much in the advanced illness and serious illness space. And so obviously predicting someone's prognosis is really important. We will commonly use things like mortality or death as an endpoint because it's just a 1 or a 0 in the model. It's really easy to code out and it's sort of an unbiased outcome, death. The issue is that oftentimes death isn't the right outcome that matters as clinicians. Rather than predicting someone's risk of mortality, what we're really trying to predict is someone's risk of declining in a way that causes a quality of life that's detrimental to a patient, or for example, incurring a lot of symptomatic burden or incurring, for example, limited benefit from a certain treatment. Those are the outcomes that actually shift our clinical decisions much more so than someone's death. But because death is an easy outcome and it has some face value, oftentimes that's what comes up, the first time that we encounter data scientists that are actually trying to predict these models. And I think it could just be, some of that going back and forth about what the right models, what the right features could be is better done, at the outset of model development. And then, once we get the right features and outcomes, I think we can really trust a lot of the data scientists that we work with to come up with the best model.
Well, the example of the model kind of predicting every cancer patient was going to readmit is sort of almost like, I wouldn't call it a mistake of the model, but a challenge that we universally kind of face in machine learning. Even with the stationary distribution, we expect situations like that to come up where it kind of predicts something obvious, I guess. But I know in the article that initially brought you to my attention in Slate, How the Pandemic Made Algorithms Go Haywire, you cover a lot of cases where they don't necessarily have that stationary property, that we can have regime change or whatever you want to call it that messes up machine learning. Can you go into a few details about specifically the pandemic and how that's caused a few interruptions in machine learning analysis and work?
I came to this example through a very pragmatic way. I lead a project that uses a machine learning based mortality prediction tool to identify individuals who may benefit from early conversations about their goals, treatment wishes, and end of life wishes. So that's an effort that's been rolling out across our health system and has been replicated in other health systems as well. What we had noticed during the pandemic was that fewer and fewer patients were being identified, despite the fact that patients coming into the clinic, if anything, were sicker, let alone the same level of health burden. And so we were wondering why that was. And that led us down this route of actually exploring what the pandemic has done to some of the features that are incorporated in not only mortality prediction models, but predictive models in general. I think what we realized was that the pandemic induced a lot of utilization shifts in how patients were utilizing healthcare. People were coming into the clinic less. People were coming through the ED and hospitalization perhaps more, or for different reasons. And in particular, for a model that we had developed in the pre-pandemic era to predict mortality that relied heavily on laboratory utilization, since laboratories are really prognostic in cancer, people were just utilizing the laboratory a lot less. Doctors were telling patients, you don't need this routine lab lab check. You don't need to come in for this. And it was actually, we identified that almost entirely decreases in laboratory utilization were associated with shifts in the risk score downward in the model and under prediction of mortality for high risk individuals. But you can imagine there's analogies to that for any machine learning model that's based on interacting with the healthcare system. We were just utilizing it in different ways. And so models that used pandemic inputs for that, I think, were likely to be prone to drift during the pandemic. And that's what we wrote about.
So that drift, I mean, it's sort of implicit in the data. If people don't come in and get tests, then there are no rows in the database. Is there anything that can be done here from like a modeling perspective?
Well, I think there's probably two general solutions that we took away. One is, aside from model development, having robust performance tracking and tracking of outputs of the model could have clued us into the solution before it started to actually affect how interventions were deployed. We were lucky to do quarterly reviews of sort of model performance just standing before the pandemic, and that clued us into this before something perhaps more drastic were to happen. But, I think more continuous reviews, particularly around sudden shifts like this, would really be helpful. So performance tracking, I think, is one big takeaway. A second thing, though, is that I think the pandemic has taught us, at least, is to really be clued in to features that are part of the model that could be prone to drift, particularly those that are heavily reliant on discretionary utilization of services like x-rays or laboratories or outpatient visits that have the risk to essentially fall to a cliff during a self-administered utilization drop like we did during the stay-at-home orders during the pandemic. I think both proactive model planning to be aware of some of those features that could be prone to that and potentially cluing that into a model's risk of drift during sudden utilization changes, and then robust performance monitoring are the two takeaways. And those are, just as an aside, those are things that we're trying to take to other models in some of my academic work, actually predicting a model's risk of drifting during a pandemic or a sudden utilization shift and trying to essentially do stress tests for models prior to deployment, so that we can be clued into a risk of drift. Because I think being aware of the issue solves half or more of the problem.
When you observe some of those issues like, during stay-at-home orders, x-rays went to 0, it seems rather obvious once you've said it, but I don't know that as sort of a machine learning practitioner, I would have figured that out on my own. Maybe through my exploratory data analysis, I would have uncovered that, hopefully. But I guess my question is, in the overall effort, who do you think holds the responsibility? Should a doctor be letting the team know that this is the facts of the matter, or should a machine learning practitioner be finding that cliff?
I think it's really unreasonable to expect machine learning practitioners who have limited clinical knowledge to be aware of which factors may be prone to drift, or even more broadly, which features may be prone to bias. Ultimately, it's the responsibility of clinical lead behind an operational machine learning platform to be aware of what features may be prone to bias or drift and to clue those into the machine learning practitioner so that we can run some of these stress tests of what would happen if we didn't include some of these features, or what would happen if we used a shorter look back window for some of these features that could not be prone to so much drift. How would that affect model performance? If I had known about the pandemic when we developed our own machine learning model, I mentioned in this example, I would have seen, well, how much is model performance actually affected if we didn't include so many features that were related to laboratory utilization, or if we use different time windows for laboratory utilization, because we could have potentially developed a more robust model that was robust against some of this drift. And so that would have been, I think some of that responsibility is up to the clinical leads that are responsible for identifying some of the features of the model. But on the other hand, it's up to the machine learning practitioners to loop the clinical leads into the model development process early so that we have that opportunity.
You'd mentioned doing a quarterly review process of your existing models. Could you describe what that process is like?
Well, most of the time prior to the pandemic, it was pretty quick. We were looking at how many patients were flagging as positive, how that changed over time, and whether there were any robust shifts up or down. And usually our model performance compared to our initial prospective validation of the model were pretty similar over time because not much in the input distribution was changing. So those meetings used to take only 5 minutes or less prior to the pandemic. It was just a simple check. Now, I will say that as some concerns in other algorithms that had come out around algorithmic bias and systematic mischaracterization of risk for certain protected groups of individuals had come into the literature, our meetings got a little longer as we were looking at some of that in the model and looking at potential bias towards marginalized groups. But they still used to be short meetings. During the pandemic, when we started to see this downward and sustained downward decline in risk scores, that's when we started to get clued in to it. And you could argue if we did more frequent meetings, or if we had recognized that this would be an issue, we would have done more frequent meetings than just quarterly so that we could pick up on this beforehand. But that's kind of how the cadence of those meetings work.
Thanks to our sponsor, mParticle. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit success, such as data quality, data governance, and connectivity. mParticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customers' data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose mParticle. Visit mparticle.com to learn how teams at Postmates, NBC Universal, Spotify, and Airbnb all use mParticle's customer data infrastructure to accelerate their customer data strategies. That's mParticle. Better data, better decisions, better outcomes. Visit mparticle.com to learn more. On Data Skeptic, we talk to researchers, scientists, and entrepreneurs working to drive real innovation in using data-driven intelligence. From forecasting weather patterns to anticipating stock market movement, we've heard a lot about the many exciting and ingenious methods used to pave the way towards insight. But to unlock the promise of advanced analytics and machine learning, you're going to need a data warehouse. That's where our latest sponsor, Astera, enters the picture. Their no-code platform gives users all the tools they need to bring together data from disparate applications and systems, cleanse and enrich it, then consolidate it on the cloud or on-premises. Astera is focused on user experience, automation, and being a comprehensive ETL pipelining solution that fully empowers domain and data experts to take charge of their journey to insights and craft a solution that meets their needs. The resulting process is fast, agile, intuitive, and most importantly, future-proof, so your data warehouse is always ready to deliver cutting-edge reporting and analytics. To find out more about the Astera platform, get in touch with the team at astera.com/contact-us. Astera is Astera, astera.com/contact-us. So a lot of these findings really make us think, I think correctly so, that if there's a big change like the pandemic or some other future event that's unexpected, models kind of become suspect because they were all trained on historical data, which of course couldn't include future data. But it does seem to present like kind of an operational conundrum. These models were useful in practice, so should we keep using them because they've been useful, or should we, because of the risk that they've gone bad in some way, just abandon them entirely? How do you answer a question like that?
It's so dependent on, one, the experience you've had with the algorithm, and two, the importance of it in the generalized use case. So in our situation, using mortality prediction tools to help guide advanced care planning, we had the advantage that this model was baked into the process of care across our health system for at least a year before COVID even happened. And so clinicians were used to using this tool. It had resulted in a tremendous uptick in rates of conversations, let alone downstream patient-centric outcomes. And so there was sort of operational priorities towards using the algorithm and getting the process right, as opposed to just abandoning the thing altogether. Contrast that with an example that we wrote about in the article, a big credit card company deploying a fraud detection rollout immediately around the timing of the pandemic. That model hadn't been rolled out yet. It was a little unclear as to how, even in a normal state, how it would affect detection of fraud and the process of operationalizing fraud detection. And so before it was even rolled out, the pandemic happened and they noticed that performance in the background was declining for the model. And so they delayed the rollout. That was an example of where they didn't even deploy it or delayed deploying it because of the pressures that the pandemic focused on. I think it largely just depends on how much the healthcare system is dependent on the model, its familiarity with it, and then what the urgency of the use case is. But I would argue that during the time of the pandemic, if you were thinking about deploying a model, taking a month and actually seeing how robust your model was to the pandemic and what changes could be made would be a really good use of time. Unfortunately, sometimes we're guided towards speed when it comes to some of these things rather than getting it right. And I think that tends to be an issue in issues like this one.
The use of fraud detection is an interesting one. Like, I think one experience a lot of people have had is if you don't let your credit card company know you're traveling, they might flag your card in another city because they're not used to you being there. And then, of course, we're not traveling during a lot of the pandemic, so that feature is no longer useful. In the medical use case, it's not super obvious to me how a feature goes bad. I mean, if I have cancer today, I have cancer tomorrow, unless it's cured or whatever. And you've touched on some of these, but would you mind sharing a few examples of what types of features are most susceptible in medical cases?
I always use the example of cancer screening because I think cancer screening is the perfect corollary towards the situation that you just described in fraud detection. So during the pandemic, we were actively telling people if you're having an elective colonoscopy, if you're having an elective mammogram, if you're scheduled for one, let's push it off because we don't want to expose you to. This was a systematic policy that not only clinical societies, but health systems were enforcing. They were just shutting down the endoscopy suite for colonoscopies. They were shutting down the mammography suite. And so when you think about it, what does it take to get a cancer diagnosis? Well, either you get it detected in a curable setting from a cancer screening, which is honestly how most cancers are detected in certain cancers like prostate or breast cancer, or it gets detected because you have symptoms, because the cancer has progressed to a point that you come in for something. And so what we saw during the pandemic, because of the shutdown in that feature, was that one, if you included a feature that was related to mammographic screening or colonoscopy screening, all of those features were completely sort of moved to zero during the early and even intermediate phases of the pandemic. So any model that relied on those, I think some of those became somewhat useless features. But secondly, and maybe tangentially related to the point, the entire risk distribution changed of things like predicting cancer risk or risk of dying from cancer because the people that were coming in with their cancers were so much sicker. They were sort of right shifted towards more severe cases of cancer because of this sort of artificial restriction that we placed on cancer screening during the pandemic. I just cite that as an example from my own field about how a feature went wrong during the pandemic because of something that we enforced and that we're still honestly trying to get out of. Cancer screening rates are still well below baseline and will probably continue to be so for some time.
Yeah, that's fascinating. I guess historically, if I had not had any screenings, that was sort of a good corollary. It means there was nothing urgent where a doctor gave me the order to get the screening. But all that changed suddenly. We have that insight. Machine learning doesn't directly have the insight. Should we go in and try and hack the model and bake that in? Or do we just abandon it and retrain? I guess how do we approach this new regime change?
I think it's really difficult to anticipate a priori. We argue in the piece for being aware of which features might be predisposed, but I think it's really difficult sometimes to identify which features might go haywire. So a priori sort of mitigation of some of this, I think is going to be a little tricky if I'm being honest with myself. Going back and hacking the model, I think is a reasonable idea once you've identified that the model's performance has drifted somewhat, because at least you can, if you're committed to deploying the model during the pandemic, at least you can come up with some sort of a fix during the immediate time that gets around the issue. So for example, in the cancer risk model, perhaps we try to de-weight some of the features that manually de-weight some of the features that are related to cancer screening because of what we're seeing. I think the more robust and automated solution, and the one that I am trying to work on in some of my research, but would love to partner with others on, are actually developing self-learning models that not only detect drift as things are happening, but also identify those features in automated fashion, sort of adjust some of the weighting or the refitting of the model for those features that are most prone to drift so that we can still be aware of things as they're happening, but we're not trying to retrofit models on the back end in somewhat of a haphazard way. And if we can develop some of those self-learning models, and I know things like reinforcement learning and other types of methodologies have been proposed in this regard, I think that's the best way to not only account for big changes like the pandemic, but the smaller changes that we might not even be aware of even when they happen.
Well, I know we've talked about that human in the loop is probably an important piece of this. Even as reinforcement learning might take off, there should still be someone, a clinician, kind of overseeing things. But we also want to bring them the best model we can bring them. Do you have any recommendations for practitioners on how to best make their systems more robust or more prepared to deal with sudden change like this?
I think setting up routine audits for model performance and detection of drift is absolutely a priority. I think the second thing is oftentimes when it comes to operational ML, we tend to rely on really simple, off the shelf supervised machine learning models like automated ML solution that does its own hyperparameter optimization and cross validation, and just you plug in a data set and the model figures it out. But I think investment in perhaps more sophisticated models that do some of the self-learning process, and concomitantly investment in some of the research that can commercialize some of these self-learning processes, I think is going to be really key and will ultimately pay dividends down the road. So perhaps doing the thing that's right and not necessarily the thing that's quick, I think is another lesson learned and something that health systems and machine learning practitioners can take in. I think the third thing is triaging the level of oversight to the intensity of the downstream decision that's meant to be made. So in our example, the model was tied towards having a conversation. And arguably, everyone that walked into our clinic should have a conversation about their own treatment goals and wishes. So the fact that model drift was potentially resulting in less conversations, well, it's not the most life or death type of decision. And so ultimately, we decided to try to keep the model going, but try to retrofit a better model on the back end. But say, for example, a similar model was being used to triage who gets a ventilator in the hospital, or who gets sent for an immediate stent procedure in the heart attack suite. Those are things that can really, and in the moment decision, can be life or death for a patient. It's important to be aware of what the model is doing in real time, but if there's even a sense that the model could be reinforcing biased decisions, then I think it's imperative upon the health system, upon doctors, upon machine learning developers to say, let's put a pause here and rely on clinical judgment when it's necessary, but let's put a pause on implementing a model that could be doing really bad things for patients. So those would be some of the lessons learned, I think.
Many machine learning systems, maybe not reinforcement learning all the time, but most of them require some sort of retraining from time to time. Or at least you train them the first time, probably you retrain them again later. Do you have any advice for what the appropriate cadence is for doing a retraining process?
I would argue that most clinically operational machine learning is not doing the systematic retraining and model recalibration that you're speaking about. We need to develop some best practices here. And I don't think that retraining and recalibration is necessarily happening on a robust basis in most of the time that clinical predictive models are being implemented. So that's step number one. In terms of the cadence of how frequently this needs to be done, I think certainly when there is a detection of real-time changes in feature distribution or utilization related inputs, that should be sort of a just-in-time retraining. But healthcare and model feature availability, especially for things that are utilizing the electronic medical record, oftentimes changes every 6-month or annual basis. Sometimes a really important feature will only come online after the model has been trained. And so, I think a pace, if I had to put a number to it, of every 6 to 12 months of being systematic in retraining a model and seeing how that improves its performance over time, I think is really important. Oftentimes in clinical medicine, we have a tendency to want to implement things that as they have been published in papers, because we don't want to futz around with models too much when they have proven performance. And so a lot of the time, the models that have been deployed are sort of fixed over time because that's the way they were deployed and studied. But I think with machine learning, we ought to be a lot more flexible and recognize that oftentimes the best model is going to require some recalibration and be a little bit different than the model that appeared in your peer-reviewed publication. And I think once we get in that mindset in clinical medicine, we'll enable a little bit more flexibility towards these applications and better patient care.
Well, there's no doubt we've seen a ton of successes in deploying machine learning for clinical use cases like the ones you've described and so many others, but I also can't help feel like we're in really early pioneering days and there's still a tremendous amount of opportunity here. Do you agree? And if so, do you have any advice for someone looking to get into it?
For people who are looking to get into machine learning, particularly I can speak from the clinical side, from clinicians who are looking to develop machine learning models for clinical care delivery, it's really important to first off identify the specific outcome and specific use case that you'd like to get into and start talking to data scientists in your institution who are responsible for things like electronic health record deployment or for routine analytics in the hospital. Those are going to be the folks that you may often not even know their names, but who are going to be the most important for developing models that can actually achieve impact. So I think getting people talking together, in my case, trying to get out of just the research frame of mind that I've been primarily focusing on over my career and sitting in on operational meetings, sitting in on meetings from our predictive healthcare working group and getting a sense of where there is actual alignment towards not only data availability and availability to predict a certain outcome, but also just leadership buy-in and a general sense of energy around the motivation to develop an algorithm-based solution. I think that's where the most successful models are allowed to move forward and where the most successful use cases are moving forward. Just an example for the mortality prediction advanced care planning use case, that would have never gotten off the ground if we didn't have leadership, in particular our chair of hematology oncology, Lynn Schuchter, who was completely dedicated towards improving communication around serious illness for patients with advanced cancer. And if we didn't have that motivator, then the entire process of developing an algorithm for impact would have never gotten off the ground. So I think finding that sweet sauce and really latching yourself towards targeted use cases and talking to the actual model developers, if you're a clinician, or if you're a model developer talking to clinicians, I think is really useful for getting things off the ground.
In terms of your model, can you frame it in terms of its inputs and outputs? What do you provide it, and what's the ultimate suggestion or recommendation or label it applies that a clinician can look at?
The model features for our mortality prediction tool are largely structured electronic health record variables that fall into a couple of general domains: demographics, laboratory features, comorbidities, and certain cancer-specific utilization-related features like radiology utilization, for example. So we take a series of those inputs. When the model was trained, we reduced the number of features to those that were sort of essential. And then through a gradient boosting model, we predict risk of 180-day mortality, which was our surrogate for need for a timely conversation. So that we predict on 180-day mortality and then generate lists of high-risk patients as part of a general behavioral intervention that includes peer comparisons, performance reports, and then opt-out text message reminders for patients that are deemed high risk by the algorithm that essentially reminds a clinician to have a conversation at the point of care. So that's the intervention that we've developed and has been pretty successful, deployed since 2019.
Is there anything significant to the 180-day parameter?
That was actually determined through conversations with clinical end users about what would be a long enough time window that we wouldn't identify people who were just too sick to change their trajectory of care, but a short enough time window that they could actually benefit from a conversation that the outcome of mortality would still be relevant. Because if you're predicting 2-year mortality, for example, then it could be that 80% of the patients who walk into a certain pancreatic cancer clinic would flag as positive, but you wouldn't really know what to do with that at the point of care because there's just so much volume of individuals who would flag as positive. So we really tried to use some clinical end user insight in determining that.
Ravi, is there anywhere people can follow you online?
Sure, you can follow me on Twitter at Ravi_B_Parikh, or you can follow my website, ravibparikh.com. And happy to talk to anyone who's interested in exploring some of these matters around performance drift or other aspects of implementing machine learning in clinical care. We're actively seeking collaborations to get beyond our own health system to deploy some of the lessons learned, and particularly in bringing principles of behavioral economics, implementation science, and mixed methods research to the model development process to actually generate solutions for impact.
Well, very exciting work. I look forward to following it myself, and we'll have links to all those things in the show notes so listeners can too. Ravi, thanks again for taking the time to come on Data Skeptic.
Sure, and Kyle, thanks for the opportunity.
That concludes another installment of Data Skeptic Physically Distributed. Thanks to our sponsors, mParticle and Astera. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, show notes written by David Abembe, and our host, Kyle Polich.